Okay. So this is a second example. Let's take a space Q equals X, Y, Z, and W such that X minus Y equals 0 and let's say Z minus Y minus W equals 0, okay? And for any numbers X, Y, Z, and W. So again, we have a linear system, and we have 4 components. And so we proceed the same way of asking for, we want to find a basis. And here we have, so let's write out these equations as a in fact, though, let me write this as, let's say, Y minus Z minus W. So the order we're going to have is X, Y, Z, W. So I'm going to list them. I could keep the thing the same and have minus Y plus Z, but let's just leave it like this. Okay, so my equations are X minus Y equals 0 and Y minus Z minus W equals 0. And again, I've managed to write something in echelon form so that X and Y are leading and Z and W are free, right? So we want to find X and Y in terms of Z and W. So we can solve the second equation, see right away that Y equals Z plus W, and X equals Y, which then equals Z plus W. So we have X equals Z plus W and Y equals Z plus W, right? Okay, so we can write then, we want to parameterize Q in terms of free variables, which means getting rid of so here's the parameterized form when I've gotten rid of the leading variables X and Y in terms of the free variables Z and W. And then we want to write this as a span. So there's a trick to doing this in which we could sort of write this up. There's a longer way that justifies it, but the trick way to do it is to pretend that one of the variables is 0, like pretend the W's are 0, and then write Z times the coefficients of the remaining ones. So if I thought of W's as 0, I'd have Z times 1, Z times 1, Z times 1, and Z times 0. So the coefficients here would be 1, 1, 1, 0, right? Then you do the same thing for the other one. I pretend the Z's are 0 and do the W's, which would be 1, 1, 0, 1, like that, such that Z and W. So that's a trick for just, I could write this as Z, as you know, Z plus 0W, and this is 0Z plus W, then sort of decompose this into a sum. And so this is just elementary vector addition. You can check this true by just reversing and just multiplying the Z in here, multiplying the W here, and adding them together, and you'll get this vector. Okay? So but the result is that Q is written as a span. So we can see that Q equals the span of B, right? Where B equals 1, 1, 1, 0 and 1, 1, 0, 1. Okay, so this is a candidate basis because it spans the space. Now, it turns out these vectors are linearly independent, as we can see from, if I do the linear independence test, 1, 1, 1, 0 plus B. So to do that, I suppose that 1, 1, 0, 1 equals 0, 0, 0, 0. And I want to show a goal. Show A equals B equals 0, because if I can show that, then they're linearly independent. And you can see, just looking at this from the third equation, is reading off is going to be A plus B times 0 equals 0, therefore A equals 0. And the fourth equation is A times 0 plus B equals 0, so B equals 0. So indeed, this check, we found that this supposition implies this result, so B is made of linearly independent vectors. So we can choose a basis. Let's choose sort of B1, which equals the sequence 1, 1, 1, 0 and 1, 1, 0, 1. And we could also look at we could also look at the matrix of this one, but let's go and ask a slightly different question, because we could go through and find, because we could choose any matrix, but let's go and do a slightly different problem at this point, which will lead to the same concepts as before. But we could ask, is 3, 4, 5 a member of Q? Is this vector in Q, right? So how would I deal with that question? Well, what does it mean to be in Q? Well, it means that Q, since Q is a linear combination of these two vectors, it means I have to find a linear combination that equals this vector here. So to answer this question, what we want to do is we have to solve a linear system. We have to solve the linear system that A times 1, 1, 1, 0 plus B times 1, 1, 0, 1 equals 3, 3, 4, 5. Now, if we can find a solution, it's in Q. If there's no solution, then it is not in Q. Now, there's a theorem that says for any basis, any vector has a unique solution. So because this is a basis, we know there's either going to be 0 or 1 solutions. We're not going to get a free variable possibility. We're going to get a contradiction. We're not going to get a free variable because this vector only has a unique specification in terms of this thing. So now this one, we can write, this is the vector form of a linear system. Now we can convert it to a different form. We can convert it to a matrix form. in the following way. We take the columns here as the columns of the matrix 1, 1, 1, 0, 1, 1, 0, 1 times AB equals 3, 3, 4, 5. Okay? So this is the matrix form. However, since this is not a square matrix, the concepts of inverse matrices don't apply, right? So we're not. So if we wanted to solve the problem of this, we can't use an inverse form because this isn't a square matrix. We can look at this matrix and do various things and see what its rank is and stuff like that. But to solve the system, what we want to do is we're going to come down from the matrix form here and make the augmented matrix, which is, you can see more clearly from the matrix form, is the following: the augmented matrix, which is not the matrix equation, it's just a matrix. But it enables us to solve for A and B using Gauss's method. So here's the augmented matrix. 1, 1, 1, 0, 1, 1, 0, 1, vertical bar for augmentation, 3, 3, 4, 5. Okay. So then we apply Gauss's method to this augmented matrix, and we'll find this, whether there's a solution for A and B. Well, let's do that. So let me start over here and give myself more space. That we can see that what we want to do is we need to sort of make this into, get 0 here, so we could do minus row 1 plus row 2, minus row 1 plus row 3, and that'll clear the first column, and let's see what happens then. So I don't change the first row. The second row is minus row 1 plus row 2. That's clearly going to make a 0 row, right? Because these two are identical. The second one is going to be minus 1, it's going to get a 0, but I have minus 1, I'll have a minus 1 there, and 3 minus 4 is 1 there. And I haven't changed this. Okay, so now I have to do two things. I have to put the 0 row at the bottom formally to be an echelon form, and I have to get rid of this one of these. Probably the simplest way is to do row 3 plus row 4, which leaves these alone. And then as 0, minus 1 plus 1 is 0, and 1 plus 5 is 6, right? And then formally to put it in echelon form, although it would be to swap row 2 with row 4. 1, 1, 3. No, actually, what I want to do is, let's see. Is there any way to do it with 1? I don't think so. Okay, so yeah, so I'm going to have 0. There's no way to do it with a 1 swap, I think. And then I have to do another swap formally of row 2 with row 3 to get 1, 1, 3. 0, minus 1, 1, 0, 0, 6, and 0, 0, 0. Well, that's a lot of work to realize, to then find that in the third row, when I take the third row here, that equation is going to be 0 times b equals 6, which is the same thing as 0 equals 6. That's a contradiction. And what that means is that there's no A and B, there's no solution. So I can't solve the linear system. Here, there's no solution for A and B. That means that 3, 3, 4, 5 is not a member of Q. And we could it's just not a member of Q. So that is, we could go and find other, we could find other vectors that were like probably 3, 3, 4, 4 would be okay. But let's look at this matrix here and see what we can see with the coefficient matrix with 1, 1, 1, 1, 1, 0, 0, 1, and ask, what is the rank? Let's call this M, let's call this N, rank of N. So we could choose either the row, we could choose either the row space or the column space. Now, we already know that this is the result, right? So if we just take over here, we know that the echelon form of this matrix is one echelon form is 1, 1, 0, 0, 0, 0. Right? So the echelon form, if you do the same row operations up here on this side, and you'd get this. So therefore, the rank of N equals 2, because 1, 1, 0 minus 1 would be a basis for row space, because we could say basis for row space is 1, 1, 0 minus 1. Okay, well, that's okay, so that's maybe there's another example.